This lecture is part of a series of lectures for Rad229 MRI Signals and Sequences offered in the Department of Radiology at Stanford University. The 12th lecture, Pulse Sequences Part 5, is broken down into 3 parts, and Lecture-12B covers Gradient Waveform Design. The learning objectives for this lecture include being able to compare analytic and optimization approaches to defining gradient waveforms, to understand the steps needed to define slice select, phase encode, and frequency encode gradients, to appreciate the challenges and details behind designing gradient waveforms to meet several constraints. Gradient waveform design approaches can be broken down into at least 2 categories. The first includes so-called analytic expressions, that is, algebraic expressions that take into account all of the considerations required in terms of gradient amplitudes and hardware constraints. These lead to simple waveform shapes that are typically trapezoids and triangles, and in fact they're not available for many constraint combinations, which makes this approach somewhat limited. It does have the advantage of being precise, they're analytic expressions after all, and of course being fast, because they're straightforward to compute. In general, however, they're also only applicable for single-axis solutions, although multi-axis solutions are possible. And so on the bottom here, we see a series of gradient and RF events that were designed using conventional analytic expressions. And you can see that the resultant gradient waveform shapes are typically trapezoids and triangular in general. Another possible approach is to use a so-called optimization algorithm, an approach that takes into consideration several constraints that we'll discuss in the next slide, and uses a numerical solver to design the gradient waveforms. This can enable designing gradients that are of arbitrary shapes and can lead to time-optimal and SNR efficient solutions, subject to hardware capabilities. This can also account for numerous constraints simultaneously, including quite complicated constraints. However, the precision and the computational time required to execute these approaches both remain challenging, but multi-axis solutions are relatively straightforward. So in this example on the bottom here, this is a time-optimal phase contrast MRI sequence that was designed using numerical optimization approaches. And you can see that many of the waveforms end up being non-traps and non-triangles, and that is a result of scanning up to the limits of the available gradient hardware while doing so in a time-efficient manner. And so you can see that the gradient waveforms overall are substantially faster and don't take as long to play as the similarly designed analytic trap and triangular gradient waveforms. So we saw this in the previous lecture that gradient waveform design involves meeting certain goals subject to many constraints. And those goals may include spatial encoding, generating the proper or desired image contrast, perhaps motion encoding, and of course speed and SNR efficiency are oftentimes important. The constraints are many and include things like gradient hardware constraints, physiologic constraints, perhaps field imperfections that you might want to correct for in design. And in this lecture, we'll talk some about pulse sequence constraints, the constraints that are accorded into our pulse sequence as a consequence of choices of field of view, bandwidth, and perhaps first moments. In principle, all of these things can be designed for even simultaneously, but as the complexity increases, that is, the number of constraints under consideration increases in number, optimization methods are generally needed. And for many problems, analytic expressions simply are not available or not possible. So let's consider the gradient waveform design problem again, where the goal is to achieve the shortest TE or TR. And again, we have several constraints that include hardware, RF pulse, slice thickness, resolution, field of view, and the receiver bandwidth. These constraints are generally enough to specify the timing considerations for a spoiled gradient echo sequence shown below. Amongst the first things we can consider is how to design the gradients to encode appropriately for the field of view of interest. And in MR, we can actually pick the field of view in 2 directions, say the two in-plane directions that we might call the X and Y directions. When thinking about the X direction, which is oftentimes synonymous with the readout direction, the field of view is constrained during readout according to the amplitude of the GX gradient that's possible and the raster time stepping of the receiver system, which is defined by the receiver bandwidth. In the KY direction, the delta KY step in this case is defined as 1 over field of view in the Y direction, and it has a similar relationship, but depends this time on the delta gradient step and the duration of the phase encode gradient. So very similar expressions, but they have different consequences when it comes to designing the gradient waveforms for this particular pulse sequence. So how do we design phase and frequency encoding gradients in particular? We'll walk through some steps required to do so. So when it comes to designing the phase encoding gradient, we can think about how we design the specific phase encode steps. We start by calculating KY max from the number of defined phase encode steps, and that's typically equivalent to the resolution that you're interested in achieving, and given a specific field of view. So this helps us define the largest phase encode step, for which we need the largest encoding gradient. We can then design the shortest duration phase encoding interval that is needed to achieve the gradient area necessary to reach KY max. And then we can linearly scale that designed gradient area for all of the other steps. And by linearly scaling the area, that keeps the sequence timing constant from TR to TR. So you can imagine that the phase encode gradients could be smaller in duration for the early phase encode steps near the middle of K-space, and they increase in area, perhaps duration, as the sequence progresses to the edges of K-space. But that's generally not desired because we'd prefer to keep the TR constant for the purposes of maintaining the signal and image contrast that we have in mind. So we can use the equations from the previous page to define the delta KY as a function of the delta gradient step and the duration of the phase encode gradient. We know that KY max is related to the number of phase encodes divided by 2. We offset a little bit for integers and multiply by the KY step, which is equivalent to the gradient step and the duration of the gradient waveform. So now we can simply solve this algebraic expression, perhaps using the maximum available gradient amplitude of the system, and then calculating the according phase encode duration itself. And as a consequence, we would see that for an encoding resolution where the peak KY max is 4.95 inverse centimeters, imaging hydrogen using a 4 Gauss per centimeter gradient amplitude, we would need a phase encode duration of about 290 microseconds. Now, this would help us design both the amplitude using Gmax and the duration that we calculated here to design a phase encode gradient area. But we also have to take into account the ramping area, the duration of the ramps themselves. And so in practice, this precise approach doesn't really work. Ramping to the gradient phase encode maximum adds some additional M0. And so in fact, it's better to design in the space of M0. We won't go through those steps now, but you can appreciate the small details will really matter in terms of making sure you encode the right KY lines. Let's now turn to designing the readout gradient, and we have under consideration the use of a high receiver bandwidth. This accords with a high range of frequencies used to encode across the field of view and then subsequently received by the receiver system. High receiver bandwidths require stronger gradients that produces a larger range of frequencies across the field of view, or in fact across each pixel. Higher receiver bandwidths consequently produce less chemical shift. There's a larger frequency range per pixel, and the shift for off-resonance species like fat is smaller as a percent of that frequency range, and consequently they shift less. This will result in lower signal to noise when we use high receiver bandwidth because we typically have shorter acquisition times. And that's a consequence of moving across K-space faster with a stronger gradient, but this does afford us a slightly shorter TE as well. And so here we're just demonstrating there's a range of frequencies across the field of view that are governed by the applied gradient. And a stronger gradient, as shown with the dark red line here, will give a stronger, larger range of frequencies, and that accords with using a high receiver bandwidth. So the readout gradient amplitude can be calculated from the known receiver bandwidth and the field of view, and those are typically the parameters that the user would choose on the scanner. And so we're left to design the gradient amplitude maximum. Algebraically, we can solve this expression to see that we need about half a Gauss per centimeter for, in this case, a field of view of 30 centimeters and a received bandwidth of plus minus 16 kilohertz. And so what's left to define is the readout gradient duration. It's important to remember that the readout gradients, or all gradients, are played for finite intervals that accord with the frequency response of the gradient amplifier system itself. In this case, we specified a frequency of 32 kilohertz, and so we can define the time step required, or the duration of each time step during sampling, and this works out to about 15 microseconds. And if we go back to considering the number of read points that we wanted to acquire, and let's say that n read was 128 points, then the duration needed to read out is 128 points times this 15 microseconds, and that gives us about 2,000 microseconds of readout gradient amplitude duration. And so again, the combination of amplitude and duration specifies largely the readout gradient. What's left to define is then the ramps. We won't take the time to do that now, but that would largely specify the readout gradient waveform. So at this point, we haven't talked about the first part, which is the slice select gradient, and we'll spend the remainder of this lecture talking about some details of designing the slice select refocusing gradient. And again, our goal is generally the shortest TE/TR, subject to various constraints, including the hardware, RF pulse, slice thickness, resolution, field of view, and the receiver bandwidth. You'll recall from earlier lectures that the excitation frequency that we need or use in our RF pulse will determine the range of spatial positions that are excited by the exciting pulse, scaled according to the applied gradient strength. And so the applied gradient is demonstrated by this purple line here, which linearly relates the excitation frequencies in the positions that would be excited. In general, the time bandwidth product of an RF pulse might be defined for us, as well as the duration of the RF pulse. And so what's left to calculate then is the excitation bandwidth. In this case, if the time bandwidth product is 4 and we use a 1 millisecond RF pulse, we have a range of excitation frequencies or excitation bandwidth of about 4 kilohertz. We can then define the amplitude of the slice select gradient if we know the excitation bandwidth and the slice thickness of interest. And in this case, we choose a 10 millimeter slice thickness. And for this particular 4 kilohertz pulse, we use the constants for water and some scaling coefficients to determine that the amplitude of the slice select gradient would be about 0.94 Gauss per centimeter. So at this point, we actually know the duration of this gradient as well, because we specified it in terms of the duration of the RF pulse. So we know that this is a 1 millisecond gradient at 0.94 Gauss per centimeter. And so we could ask ourselves, well, how do we design the ramps that enable us to reach this slice select gradient that we need? So given the slice select gradient amplitude that I'm showing here and the duration of the RF pulse, that would actually just specify the purple area here of the gradient, which is the gradient that's actually needed during the active process of slice selection. What we need to also consider, however, is how we ramp to achieve that gradient amplitude. And so we can think about the delta gradient increment that we can achieve, which is related to the slew rate dotted with the delta time of the gradient raster, or the gradient amplitude step size. And these gradient amplitude step sizes, the raster time here is typically on the order of about 10 microseconds, and our slew rate max is on the order of hundreds of Tesla per meter per second. So taken together, we can estimate the incremental step size in the gradient amplitude per gradient raster step. Now, of course, we can only increment in an integer number of raster steps, and so it's important that the total number of steps taken should allow us to reach the gradient amplitude that we need. If in fact we're not quite that lucky that we don't achieve this target, we may overshoot the necessary slice-select gradient amplitude and consequently excite a different slice or a different range of frequencies. And so then we actually have to derate the delta G max, that is, derate the slew slightly, so that we exactly and precisely hit our gradient slice select amplitude in n integer steps. So what about the refocusing gradient? We've talked about how to design the ramps, how to design the area, and if we ramp up, then we know how to ramp back down to 0. We also need to think carefully about how to design this refocusing gradient and to do so in a time-optimal manner. So we can think of this as just being a monopolar gradient, and conventional monopolar gradient waveform designs arrive from analytic, triangular, or produce rather, analytic or triangular trapezoidal shapes. They're easily designed independently for each axis, and the shape is basically predetermined by the gradient maximum, the slew rate maximum, the M0 that you need, and then the step size, the temporal step size of your gradient system. On the right-hand side here is some pseudocode that describes how you basically make the decision between designing for a triangular gradient, and this may be sufficient if you only need to design a slice-select refocusing gradient with a relatively small amount of M0. But depending on the features of that original slice-select gradient, you may in fact need to refocus with a larger trapezoidal gradient. And so the pseudocode here just steps through the process for decision-making between whether or not you need a triangle or a trapezoidal gradient. And it uses the seal function here to ensure that the steps that are taken accord with the raster, with the gradient raster time as well. And this code is relatively easy to implement, and we'll look at some examples in the live lecture. So the pros of this kind of the pseudocode approach here, which I would call an analytic approach because we can describe it precisely, is that it's computationally fast and it's always essentially always going to work. The cons are that, in fact, it's not always time optimal, especially when these gradients perhaps overlap with other gradients. And we'll look at some interesting examples later, but you can imagine that the slice select refocusing gradient, the phase encoding gradients, and the readout pre-phasing gradients are all overlapping. And if we have to take into account slice obliquity, then it's important not to overrange our hardware. And so we really do need to design all of these gradients simultaneously subject to their individual constraints. And so these analytic approaches that work on a single axis may not work well when you rotate into the logical or image coordinate system. So this can be hard to combine with other gradient axes. So what if we wanted to do something more than just refocus the phase through plane after excitation? What if we wanted a flow compensated slice select gradient? Well, first question you might ask is, why would flow compensation be needed? One reason would be to limit flow artifacts from pulsatile or steady flow, and the other would be to enable off-resonance phase estimates. And the reason we might want to estimate off-resonance phase estimates would be to enable flow encoding. So flow encoding would enable us to do quantitative velocity mapping of moving spins like blood. And in fact, this is oftentimes used specifically for through-plane flow mapping. That is, we want to estimate velocity as they move through the slice, perhaps thinking that is the Z direction or through slice direction. We saw these examples earlier in the motion encoding series of lectures where magnetic resonance imaging, of course, can acquire nice magnitude images, but there's important information that's stored in the phase. And if we indeed design the first moment of our gradients, we can design the phase to be sensitive to flowing spins or insensitive to flowing spins. And in this case, we can see here in the aorta that we're sensitive to flow such that we can estimate the velocity at close to 150 centimeters per second at the peak of the cardiac cycle in this particular region. So a useful clinical technique that benefits from quantitative imaging coding. So you'll recall from the motion encoding lecture that what was necessary here to be flow compensated, for a gradient waveform to be flow compensated, was that the 0th moment was 0 and the first moment was 0. And this would ensure that spins that were either flowing or static returned 0 net phase. And the other possibility was to do so-called flow encoding, and to do so you needed a gradient waveform that looked something like a bipolar, which would have a 0 M0 no net area, but would have a non-zero M1. And the consequence would be that a phase that was indeed static would accrue phase and then give it back, such that there was no net phase stored, but a flowing spin would in fact accumulate some phase during the application of this bipolar flow encoding gradient, and do so in a way that was linearly proportional to the first moment. So the bottom line is that we can control the first moment of the slice select gradient and thereby control phase sensitivity to flow and make it flow sensitive or flow insensitive. So how do we go about doing this? Well, the conventional flow encoding waveform design is analytic. There are some ad hoc solutions as well, but the analytic approaches are useful starting points. They'll produce triangular or trapezoidal gradient waveform additions to the slice select gradient. The algebra can in fact get a bit complicated, again depending on if we're thinking about multi-axis combinations or combinations with other gradient waveforms like phase encoding or the readout pre-phasing gradient. In general, this is these analytic conventional approaches are designed independently for each axis, and that can result in some time inefficiency. And we'll see that there's some other inefficiencies that arise from these sequences, and so we seek solutions that are ultimately the most SNR efficient possible, and that's the subject of the lecture that follows this one. So here's one approach one could consider if they wanted to design a flow encoded or a flow compensated gradient waveform. This is the slice select gradient that's used for exciting the slice, and then it's refocused and flow compensated through this solid black line gradient. You could subsequently add a bipolar gradient after that to then add additional flow sensitization. And you can do this serially, that is, you can flow compensate first and then you can flow encode later, and as long as this happens before the echo time, you could be encoding for slice through plane flow. But this approach, the sequential approach, of course, is quite slow. So a slightly better approach is to encode, to use flow comp, slice select, and a blended bipolar flow encoding, which is faster. So these gradients are just essentially blended with the earlier gradients to produce the desired moments that at this point here you either flow compensated or flow encoded, depending on what the target is. The algebra for doing so gets a bit complicated, and back in the 90s it was of course important to come up with clever analytic algebraic expressions for these kinds of things so that they could be implemented on scanners and executed quite quickly. And these analytic solutions are still useful, but as I'll demonstrate, they're no longer the fastest possible solutions under all conditions. And so we seek to work towards an understanding of optimization methods that will enable fastest possible scanning under any set of constraints. So here we use some simple MATLAB code, something we'll review in the live lecture, that just uses the conventional flow encode and flow compensated algebraic expressions to compute gradient waveforms. So on the left-hand side here, we have a flow compensated slice select gradient. You can see the end of the slice select event here, and these gradient waveforms here ultimately produce flow compensation using the algebraic expressions. Now, if we want to, rather than flow compensate, we want to flow encode a similar gradient. So we see the slice select gradient is shown here, but now we want the Vanc to be 150 centimeters per second. We can again algebraically solve for the gradient waveform events, and we'll see that we get a gradient waveform that's looks significantly like a bipolar, so it's adding quite a bit of M1, if you will, but it's also longer in duration than the flow compensated gradient alone. So it goes from about 1 millisecond to over 1.5 milliseconds. So that's a 50% increase in time, which adds up considerably when you scale it across an entire image acquisition. So what else can we do? Well, it turns out that if what you really want to do is flow encoding, it's the delta M1 that really matters. So this is flow compensated and this is flow encoded. You can in fact split the flow encoding across both of these acquisitions if you want to. And you could imagine some of this gradient activity could take place and overlap with other flow compensated events, and perhaps that ends up being shorter. So this is the same example that we just showed. This is the flow compensated gradient waveform and the flow encoded gradient waveform, again designed using just those analytic algebraic expressions. And by comparison, in this case here, and we'll go through this in the live lecture, we can use some minimization functions to actually design the gradient waveforms to produce equal amounts of M1. So here we can see that the M1 that we need is half on the first set of gradients, and an equal and opposite amount of M1 is on the second gradient waveform. And the consequence is something like this. And so you can see the slice select gradient ends, and we can play two gradient waveforms, the sort of orange or rust gradient waveform and this blue gradient waveform. And the combination after phase difference processing of those two gradient waveforms produces an M1 equivalent to the target bank that we had encoded using the flow compensated and flow encoded gradient waveform. And the advantage here, of course, is that we have two gradient waveforms, the longest of which is about 1.5 milliseconds, so slightly shorter than the gradient waveform that we had before. But you could reasonably ask, can we do better? And the answer is, of course, yes. There are ways to further optimize these kinds of pulse sequences. You can see that, or you can imagine perhaps that the perfect gradient waveform would have both of these ending at the same time point, which would help with overall sequence efficiency and maintain image contrast easily between the two sequences. So in the next lecture, we'll actually look more carefully at optimization methods will allow us to match these two gradient waveforms to meet the target, say, first moment that we have in mind for flow encoding, but do so in an SNR efficient. But we'll enable doing so in an SNR efficient manner. And for that topic, you can join us in the next lecture by clicking on the links below. Thanks so much.